Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture on the series on mineral resources. In the first lecture, we got an introductory overview of mineral resources as to what they are, control of certain fundamental parameters on the availability of these mineral resources in terms of the quantity that they are available, and the occurrence of various mineral resources in the Earth's crust. We saw that this term resource is a qualitative term used to represent a total quantity of the mineral resources of different metals and minerals. So, the resource actually comprise of the individual mineral deposits of those metals or minerals, and they do occur in the Earth's crust, either exposed on the surface or at different depths going down to even up to 5 kilometers. Now, in this lecture, let us try to get an overview of the distribution of these mineral deposits in space and time, because essentially space means we again consider the repository of these mineral deposits, that is the crust, or more precisely the upper continental crust. In this, the mineral resources of different metals and minerals, they occur. So, we give a brief recapitulation that we discussed about the certain fundamental aspects, and now let us move on to the distribution of mineral deposits in space and time. Now, before we highlight, or before we start discussing on the distribution of these mineral deposits in space, space means it is again we can recall that it is the Earth's continental crust. So, it is the Earth. So, before we go to the distribution of these mineral deposits in space, let us first consider the Earth, because the domains in which these mineral resources are enriched to give us the mineral deposits are a result of the earth processes operating at different scales, and those earth processes we fundamentally can classify in the context of mineral deposit formation. Of course, it is generally applicable to the formation of different types of rocks, and since mineral deposits are an integral part and they occur in association with the common crustal rocks. So, they are also results of the broad processes operating inside the earth. So, we generally, that is how we describe. So, when you come to the earth, so the earth is like a big machine, or we call it as the earth system, where the different components of the system they operate in a well orchestrated manner, driven by the energy. The energy has to come from somewhere. So, we have divided the processes into two broad categories, that is the endogenic and the exogenic. So, the endogenic. So, before coming to understand the endogenic process, let us recall that there are different components of this earth system. This is the this is represented as the crust, which I am representing in a very simplified manner, and this is the mantle and the core. So, the average crustal depth is about 33 kilometers, and so this is the core, the mantle, so we will have to see that when we say that the endogenous process are essentially driven by the Earth's own heat engine. So, where from this heat will come? If we begin with a originally homogeneous molten earth, then it has evolved and is still evolving in the process of loss of heat, and we know this core is essentially the metallic iron plus nickel. I am putting things in much simpler form. The mantle is silicate, mainly of iron and magnesium, and this is the crust constituted of the upper and the lower crust. And sometimes, so essentially because of the difference in the thermal conductivity between the core and the mantle, so additional heat energy always keeps accumulating on the crust mantle boundary, and that periodically is given off in the form of plumes, which are basically essentially pocket of heat energy which rises through the mantle and then melts the crust at different domains in continental as well as oceanic domain. And if we look at the diagram in a little more process oriented manner, then we know that the because of this this mantle, the lower mantle is the asthenospheric mantle, which is in a rheological state which is more liquid than solid, and there is convection going on continuously, these being the regions where the convection cell upwell, and where they upwell they give rise to situations like this. So, these are essentially the zones of asthenospheric upwelling, and where there is generation of basaltic melt by melting of this asthenospheric mantle, and generation of the ocean floor basalt, and these are the domains of the island arc, where oceanic and a oceanic plate subducts against an oceanic plate. This domain is a continental arc, where an oceanic plate subducts against a continental lithospheric plate, and this is the mid oceanic ridge. So, this is a broad framework of the tectonic of the activity, which we can explain in terms of the Earth's heat engine, the Earth's heat engine at work, mainly driven by the convection cells in the asthenosphere. And so, we will try to see, or we will try to correlate the distributional the distribution of these mineral resources in space. And in addition to that, as we have already stated, that there are situations in which the thermal plumes rise from the core mantle boundary and also cause melting at different domains in the continental and the oceanic crust, giving rise to volcanic oceanic islands, as well as the mid-continental magmatic activity, which we will see them in greater details later. But and the other process, so that is the process which is responsible mainly in distribution of the mineral deposits, because they do form rocks, and mineral deposits are associated with are integral part of the crust forming process and are associated with the common rocks in the continental crust. So, they are also a result of this broad activity which is driven by the Earth's own heat engine. Only thing that whether the scale at which we are trying to understand this process, whether this scale is the generation of the mineral deposits also happen in that scale, or there are some local scale processes which are needed in addition to that, we will be looking at them in due course of this lecture. So, the second category of process, which are the exogenic process. So, this endogenic process is essentially responsible for formation of rocks, the magmatic rocks, igneous rocks, and also the rocks which are formed by the process of metamorphism in areas where active deformation is going on with input of heat coming from different sources. The other broad process is the exogenic process, the exogenic process for which the energy is essentially provided by the sun. Now, as you could see in the diagram, the exogenic process essentially means the weathering process, erosion, transportation and deposition in sedimentary basins, normal weathering process or evaporation. These kind of processes they do operate on the surface of the earth, and the energy is provided by the sun. But as you could see in the diagram, that the endogenic process and the exogenic process could possibly be correlated, could some relationship could be established between them, because the weathering and erosion processes, denudation processes will also be depending on the rate at which the any part of the continental mass is rising. And for example, so the relationship, so the scale of the operation of the two broad processes has to be understood if we want to explain the distributional peculiarities or the distributional characteristics of these ore deposits. As I told that there are some local scale manifestation of these broad arc processes which operate in a much larger scale. So, if we want to understand mineral deposits, ore deposit formation, it is very essential for us to have a this space means essentially we mean that the earth, the continents, the surface of the earth as we see, and then we could just look at the distribution. So, here we have the globe, the physical map of the earth with the present day distribution of the land and sea. We all know that the earth is covered 70% by water, by the oceans, and about 30% are available as continental mass for us. So, let us try to first look at the distributional peculiarities of metals, just to bring out the fact that the distribution of different mineral resources are not just very uniform all across the continents, all across the surface of the earth that is all exposed to us. So, just I have taken the example, a few example of one of the metals, iron, which is available in abundant quantity and is one of the important metallic resources for steel and the infrastructure industry. So, let us look at this. This is the superior province in North America. This is the Labrador Trough. This is in Brazil, Quadrilateral Ferifero. This is the Damara belt in Namibia. This is the Barberton mountain range in South Africa. This is the two areas that are shown, 2 or 3 areas. The lower one is Dharwar Craton in India. The middle one is the Central Indian sedimentary basin, Boiladila basin, where we get iron. This is the Singhbum Craton in India, and this is the Hammersley basin in Australia. So, the purpose of showing this is that what we get, the iron ores present to us in billions of tons in quantity, they are distributed in only a few localities in the continents. They are not just this is the Krivoy Rog iron in Russia, and these are the ones which give the maximum major bulk of the production of iron in the world, and sometimes giving the quantity in very huge quantity, which we call them a super large deposit. Similarly, let us look at the distributional peculiarities of metals like copper, lead and zinc. This distribution is definitely not very exhaustive. I have only selected a few of them. This is the Chilean, this is the Andean mountain range in Chile, and we get the maximum distribution of maximum frequency of occurrence of copper deposits here. This is in the state of Quebec in Canada, where we get the famous Noranda deposit, which is copper. Here is the Zambian copper belt in Africa. Here this is the Cyprus ophiolites belt in the middle in part of the Alpine Himalayan chain. Here this is the Malanjkhand copper mine in India, Khetri copper mine in India, and this and so on. The lead and zinc deposit which are marked as black. This is the famous Sullivan deposit in Canada. This is the Mississippi region, the famous Mississippi Valley type deposit occurring in the state of Kentucky, Missouri, here in North America. This is the Zawar, Rajpura, Dariba, the northwestern India, which have produced major quantity of lead and zinc in the Indian subcontinent, and this is the Japanese island arc, which also gives very rich lead and zinc deposit. There are many more deposits, but these are the significant ones in the world which produce the maximum amount of the metals. So, here the intention is very clear, just to show that the distribution of these deposits is so very non-uniform across the continents in the world. Gold. So, this is the Nevada, state of Nevada in United States, which is currently one of the very actively producing gold of the world. This is the Abitibi greenstone belt in Canada, having very super large deposits of gold, and this is the Witwatersrand gold deposit. This is the Ghana in Africa. This is the Barberton mountain range gold deposits, and this is the one of the major gold producing areas in the world. This is the Ilgan Craton in Australia, the famous Kalgoorlie gold deposits, and here also the Dharwar Craton deposits like Kolar and Hatti. So, we can always look at and visualize the distributional peculiarities of metals. This is uranium. This is the famous Athabasca Basin in Canada. This is Jacobina in Brazil. This is the Wheatwater Strand Basin also producing the uranium. This is the Olympic Dam deposit in Australia, and this is the Alligator River deposit, the famous Ram Jungle deposit, uranium deposit in Australia. So, these constitute the major sources, major resources of the metals, where they produce bulk of the uranium of the world. And similarly, we can see the chromium. This is the Stillwater complex. This is the Skjergård complex in Greenland. This is the Bushveld complex and the Great Dyke of Zimbabwe and the Bushveld complex, and here the chromite deposits of India. We will be looking at the mineral resources in a greater details when we come to the individual deposit types. So, what we actually we are observing here, this diagram is just one such example. So, the percentage of gold total in ounce by region, this is Asia, this is whole of Africa, it is just this is the North America, South America, Australia. So, what we observe here is that the Australia, looking at the area of Australia, it contributes about 12%. Let us say take gold for example, we can look at such examples or many more of such metals which are on great demand or are very useful for our industry and are very high economic value. So, a tiny Australian mainland is contributing about 12% of the total gold of the world, whereas the whole of Asia is only about 17%, Africa is 17%, and the whole of Europe is contributing only 2%. America, taken the North America, is 34% and the South America is 17%. So, the thing which is pretty observable here is that the mineral deposits do have a very gross non-uniformity in their occurrences across the continents, and we will have to see what exactly how they can be rationalized, how they can be understood in the context of the broader earth process as we have defined as the exogenic and the endogenic processes. Look at this diagram, which is again one which was plotted, where the total number of the mineral commodities that is produced in any of the country against their area of the geographical area of the country, and this is a broad band which is defined, where it would look like the total mineral endowment is somewhat in proportion to the total geographical area of that country. Some of the countries which will be this diagram has been taken from the book of Stephen Kessler. Some of the countries would look as if their mineral endowment is far less than what would be expected from the geographical area, and some of the mineral deposits, some of the countries will be producing lot more number of mineral commodities than what would be expected from the total geographical area. So, here the situation is that it is just not the geographical area, it is definitely something more fundamental that is to be. So, the mineral resource endowment, the number of deposits and the total quantity is not in proportion to area of any continent, and as we will also see gradually that the identical geology of a region or terrain does not guarantee equal mineral endowment, and in the present day context mineral deposit occurrences seem to be controlled by global tectonic processes at diverse tectonic domain, which we will be seeing. So, now let us try to rationalize the occurrences, distributional peculiarities of the mineral resources in relation to, because the earth processes in the broadest sense could be visualized through the present day global tectonics process. Here the different plates are shown. I will be very brief. As I showed, this is the Chilean Andes, where most of the highest frequency of occurrence of the copper deposit. Also the western part of North America, which is the North American Cordillera, and regions like this is the Papua New Guinea and some of the areas, Philippines and so on. And so there is, at least we could see a very clear cut correlability that the mineral deposit occurrences are controlled by the global tectonics process. When we see the process, it is just not only so this is a subduction zone where a oceanic plate is subducting against a continental lithosphere, where this is a continental arc. These kind of domains, tectonic domain, are more akin to island arcs, where like the deposits, which what exact type of deposits we will be discussing them in due course in the lecture. It is not only just the we can make a broad correlation with the endogenous process, which basically is manifested in the global tectonics and magmatic activity within the continents or magmatic activity on continental margins. We do also have can draw some idea about the exogenous process, which are where we have the major river system, like where we have the in Africa or in South America, where the major river systems are there and weathering erosion processes are taking place in say for example, if we look at this diagram, then the areas where the weathering and erosion processes is expected to be far greater in extent or far faster. These are the areas where we have the present day mountain chains, and we all know, take the example of the Himalayan mountain chain, and we have the erosion of the Himalayan mountain chain by the river system and deposition of the sediments in huge quantity in this Bay of Bengal in the form of Bengal fan. And there are many other such areas where we can correlate the exogenous process also to, and then interesting, and another interesting process. So here is a very schematic diagram of what happens in the in respect to the process that we have just seen. This is a continental arc akin to the Chilean Andes margin, where we get deposits of copper and molybdenum. This is the continental interior, where we can have magmatism in the form of ultramafic bodies giving rise to diamond deposit. We can have ultramafic magmatism giving rise to chromium nickel deposit, and here this is something which is very similar to what is happening in the alpine Himalayan mountain chain. There are intense tectonic activity, lots of extra heat being generated through the frictional through the thrusting processes of the rock masses, and small quantities of felsic melts being generated, and there are chances of getting some uranium and thorium type of deposits, which we saw. They are the lithophile elements which generally get enriched in crustal rocks, and also in the mid continent we have tin tungsten kind of deposit. So, and this is a situation which is corresponding to the mid oceanic ridges, where the structure is pretty much complicated with faulted and fractured, giving rise to a fracture network and circulation of the sea water, and giving rise to deposits of copper, lead, zinc. We will see what exactly they are, what genetic category they belong to in due course of the lecture. And the mafic bodies which are emplaced at greater depths are also giving rise to chromium, nickel and platinum group of metals. And so these are the present day. So we ask the question that whether mineral deposits are formed in the present day or not. So these are some of the pictures which are taken from the mid oceanic ridges, like the mid Atlantic ridge or the East Pacific rise, where we see that mineral deposit formation is taking place at this point of time. These are features which are called in the sulphide chimney, which are essentially deposition of the metal sulphides, and these are the features which are very popularly known as the black smokers, consisting of very fine particles of sulphides which rise through the water column in the sea, the bottom of the sea floor. And this is a process of present day mineralization, which is, and the deposits that we discussed about in occurring in the Chilean Andes region are just about a few million years old. So, to sum up, we do have a distributional peculiarities of these resources of minerals of different metals and minerals, and that distributional peculiarities could be very well explained based on the endogenic and exogenic processes that are operating in the interior of the earth as well as the surface of the earth. So, this much for today. We will continue in the next class. Thank you. Welcome to this lecture series on mineral resources. Mineral resources are essential for the economic development of any country. Take the case of the developed countries like United States, Canada, Australia and so on. These countries, the initial phase of their economic development largely was contributed by their mineral resources, which they exploited for the development of their industry. In the Indian context, the scenario is not that very distinct as regards to the role of mineral resources in the initial phase of development of the economy, and still we lack resources of many of the important metals like the precious metals, base metals and critical metals for energy resources, and we have to largely depend on import of these metals from other countries. So, there is a need for the augmentation of the available mineral resources and for better economic development and industrial growth. So, this course is essentially a first level undergraduate level course and is taught in many universities and institutes by different course names as economic geology or geology. And in this course we will, in this lecture series, it will be more conceptual, but not involving much of mathematics. What all little mathematics we will have towards the later part, only high school level mathematical knowledge and capabilities would be sufficient. And so, let us have a brief idea. So, the concepts and facts, figures that will be discussed here have been taken from available textbooks, like the book by Jensen, M.L. Jensen and Bateman, and by Anthony M. Evans, Lawrence Robb, Introduction to Ore Forming Process, and the book by Craig Vaughan and Skinner, Resources of the Earth, Mineral Resources, Economics and Environment by Stephen Kessler, and Ore Deposit Geology by John Ridley, and Understanding Mineral Deposit by K.C. Mishra. Although we will use various other resources and other materials, and we will be indicating them in the due course of the lecture series. So, let us have an overview. So, this course is the objective of this course is to give an overview of the subject, and the very first aspect of mineral resources is the geology. So, it is basically the science of mineral deposit formation and trying to answer very fundamental queries as to how these mineral resources formed, where they formed, when they formed, and trying to understand the rationale behind availability or distribution of these mineral resources across different continents. And once we are equipped with the scientific knowledge about the mineral resources and their formation, this can be very effectively utilized for exploration of these mineral resources in areas where they are not known to be existing as of now. Another important aspect of mineral resources involves their exploitation, use of technology and different methods, scientific methods for exploitation of these mineral resources once they are discovered. Since this is not, this does not fall in the purview of geology, this is rather the activities of the mining are done by the mining engineers. So, we will not be covering much from this aspect. Then we will see these mineral resources are essentially economic commodities. We have to see how effective policies should be formulated for their exploitation in a sustainable manner, and we need to formulate proper policies for their exploitation and to sustain for the future. Mineral resources exploitation also does affect the environment in many ways, starting from the time that they are being explored, and once they are discovered, the exploitation process, the several downstream process of extraction of these metals, the various ways that the exploitation and the extraction process, downstream industrial process involving the minerals and metals, they affect the environment, the ecology, and we have to see as to how such type of effects could be at least evaluated, and whether there are remedial measures which can be taken for the deleterious environmental impact, and that also is a responsibility. And so, these are the 4 aspects that we plan to cover in this lecture series. As we all know, we can define minerals as inorganic crystalline solids. So, minerals could be, they do occur in nature, but they can also be synthesized in laboratory. So, the missing of the term natural is intentional here. We can take them as inorganic crystalline solids. They are the minerals of different metals, as we will see the classification. So, resource is an economic term. This is essential for economic development, as I have already discussed. So, now we can say that minerals which are either direct raw materials for various industries, we know what the industries are: the ferroalloys industry, the infrastructure industry, the electrical and electronic industry, transportation industry, aviation industry, refractory, fertilizer, and so on and so forth. So, all industries either directly or indirectly depend on mineral resources as either direct raw material for them, or after the metals are extracted from the minerals, they are used in different industries. So, when these two are combined, minerals which are direct raw materials for various industries and those containing elements or metals of high economic value are our mineral resources, which we will be discussing in this lecture series. We all know why metals are so much sought after. The metals, for example, the transition metals, the precious metals like gold, platinum group of metals, platinum, palladium, osmium, iridium, and many of the metals like tin, titanium, vanadium, and so on. These metals have got very special properties. Their bulk electrical, their electrical conductivity, thermal conductivity, malleability, ductility, and so many other properties which make them very special and suited for many industries, many of our products for the modern technology, and that is the reason why these metals are so much sought after. But also the non-metals, the non-metallic minerals are also equally important, as we will be seeing them. So, we can divide the mineral kingdom broadly into 2 categories: the silicates. Silicates are the common rock forming minerals making up the bulk of the crust, of the earth's crust. Often they are used as raw materials for industries such as the glass, ceramic, refractory industry, and they are constituted of the SiO4 fundamental tetrahedral building blocks, which combine in many different proportions to give the range of silicates, as you have already studied in your elementary level courses. The nesosilicate, sorosilicate, inosilicates, phyllosilicates, tetrosilicates, and so on. Some of the minerals like silica, SiO2 is a raw material for glass industry, and many of the clays are raw material for ceramic industry. The aluminosilicate, kyanite, sillimanite, and andesite are raw materials for refractory industry, and so on. And we know that they are economically important, even though they may not be as very economically valuable as the metals. The non-silicates, they mostly constitute the mineral resources as we see them here. The oxides are the hydroxides, metals like aluminum, iron, titanium, chromium, manganese, tin, and uranium, and they are either the primary minerals forming in different environments, or sometimes the product of oxidation of this kind of mineral bodies when they are exposed to the surface. And metals like aluminum, iron, titanium, the bulk of the ore minerals are the oxide minerals. The carbonates, no much of metal carbonates are important as mineral resources, but it also sometimes the primary ore minerals get oxidized in the surface in the presence of carbon dioxide to give the carbonates. Some of them, like the calcium carbonate, which constitutes the limestone, is an important raw material for cement industry. The sulfides, these constitute the most important class of the ore minerals, which we will see in a short while. Most of the transition metals and some of the other base metals and the semi metals, they do form their sulfide, their minerals which are sulfides when they constitute the resource. The halides, as we all know them, the rock salt. So phosphates, mainly thorium and the rare earth elements are available in the form of phosphates, and apatite being one of the minerals which is an important material for our fertilizer industry, and we also do look for such kind of minerals. Tungstates, it is the sole mineral for tungsten, and also the native metals. For example, the noble metals like gold and platinum, they do occur in their native form, and metals like copper also is available sometime in its native form under some special conditions. And as far as the non-metals are concerned, sulfur, which is an important resource for fertilizer as well as for many medicinal purposes, and carbon, which is essentially when it is present as a gemstone is diamond. So these are some of the examples of native metals. Now these minerals, their immediate implication that you can see from here is that whenever such kind of minerals are forming under any kind of an environment, they do indicate some of the physicochemical parameters of the environment in which they are forming. For example, for the oxides to form, we need to have an environment where the oxidation state should be favorable, or to have appropriate partial pressure of carbon dioxide to form the carbonates. And sometimes we find that these minerals, as we will be discussing the attributes of the mineral resources, mineralogy of the mineral resources constitute a very important aspect. This is one of the very fundamental contribution to science. This is periodic table of elements, which guides us in understanding the many of the phenomena, chemical phenomena anywhere. And since we are interested, or the focus of our subject is mineral resources, in formation of these mineral deposits, we can always get some insight by looking at the periodic classification of elements. Here this periodic table has been taken from the book of Stephen Kessler, where you see the elements are differently shaded. The non-ferrous metals here, the elements for fertilizer, sodium, potassium, calcium, nitrogen of course is coming from the atmosphere, phosphorus and sulfur. Here are the semi metals, arsenic, antimony and bismuth. The metals like tin and lead, germanium, tin and lead. This coinage group of metal, copper, silver, gold. The platinum group of metals, the transition metals and the rare earths. Some even though we can always go on studying it to as much minute details as possible, but to be brief, say for example a metal like chromium, it is very rigidly, it occurs in only +3 oxidation state in the primary rock forming cycle, although +6 is also, chromium also forms at +6 in different specific surface environment. So that is the reason, and this metal chromium occurs is very restricted in its occurrence, in its type of, because it forms only one ore mineral, that is chromite, and it also does form a very restricted type of mineral resource. Metals like manganese occurs in a variable oxidation state from +2 to +7, but it generally occurs at its oxides, and in mineral resources it is the manganese oxides which is recovered as the ore mineral. Metals like iron has equal affinity for sulfur as well as oxygen, so it occurs as pyrite, which is the major sulfide mineral of iron, which is iron sulfide pyrite, and also as oxide, which constitutes the major bulk of the ore. The metals like zinc, cadmium, mercury, copper and the semi metals, arsenic, antimony and bismuth are essentially, they form their sulfides. Amongst the high field strength elements like titanium, vanadium, zirconium, yttrium, hafnium, tantalum, they form their oxides, in exception to molybdenum, which forms its sulfide. And these the first series rare earth elements, the lanthanides, they form in the common rock forming minerals or as phosphate, and are important resource of, they have very interesting alloying property for which they are very much sought after for improving the magnetic field, the magnetic properties of alloys. They are very much used, very much sought after. And the classification, like say for example carbon is both a source for energy as well as for precious gems, as we know it occurs as diamond, and so on. And the fertilizer industry, construction industry, these elements which we can see from the classification here. Elements of the periodic table in context of mineral resources also are geochemically classified to lithophile, siderophile, chalcophile and atmophile. The lithophile elements they generally have the tendency to get enriched in the earth's crust or formation in the rock forming silicates. They do constitute many of the large ion lithophile elements like lithium, potassium, rubidium, cesium and so on. The siderophile metals are the ones which have the maximum, they have the affinity for iron, which is marked over here in blue. They are the siderophile elements. The implication is that during the fractionation of the bulk earth to core and mantle, when the most of the iron and nickel went to the core, many of the siderophile elements like the platinum group of metals and gold also were partitioned or fractionated into the earth's core, and that's how their availability in the mantle was greatly reduced. And as shown in the previous figure from the periodic table, you could see the chalcophile metals. So these are the ones which occur as their sulfide minerals and recovered as from nature in the form of their sulfides. Atmophiles are the noble gases, which we do not consider them in the present scenario. So, these geochemical classification of elements help us in getting the first hand information about the mineral resources, what type of minerals to expect and what kind of geological environment. This diagram has been taken from the geochemical earth reference model database. Here on the x axis the abundance, the atomic number are plotted from 1 to just above 90 up to uranium, and on the y axis the abundance of these elements in reference to silicon per 10 to the power 6 atoms of silicon have been plotted. This the zigzag pattern in the abundance of these metals is a very fundamental principle that odd atomic number elements are less abundant than the even atomic number elements, and the ones which are the most abundant elements, the rock forming elements, are shown over here. The rarest metals, ruthenium, rhodium, palladium, gold, platinum, as we saw in the previous diagram, are the rarest minerals. The blue ones are the rare earth metals, which are our which occur in much trace amount compared to the other metals, and because these are on the log scale. Now, as far as the mineral resources are concerned, the fundamental questions that we ask, that in what quantity we actually get them, and if this diagram here is, it shows the relationship. On the x axis we have the log abundance on the bulk earth bulk continental crust, where the order of about 9 order of magnitude variation, means 10 to the power of -8 to nearly 10, where you could see the abundant metals like aluminum and iron having abundances almost as 5%, 8%, 5 to 6% in the continental crust. And on the y axis the quantity of these metals available as mineral resources in terms of metric tons, and 1 ton is 1000 kg, are plotted here. That is also on the log scale. We also see that they vary almost of the under similar about 8 or 9 orders of magnitude in the quantity of these metals, starting from very scarce metal like uranium to going up to aluminum and iron, which are available in billions of tons of such resources taken all together. They are occurring in the earth. So, this diagram gives us a very first insight that the total quantity of any particular metal that is available as a resource has some kind of a relationship, direct relationship with their abundance in the continental crust. And the diagram onto the left is a vertical scale where where a term that is written here is enrichment factor, which is mentioned here, and the metals of interest are plotted on this, or are shown on this vertical scale starting from 1 to 100,000. We see abundant metals like aluminum and iron have enrichment factor values which are less than 10, we can say that less than 1 order of magnitude. What does it tell us? It tells us that an abundant metal like aluminum and iron only needs to be very little enriched to give its to be available as a resource which you can exploit, and very scarce metal like mercury, whose crustal abundance is of the order of 10 to the power of -5 in weight percent, would require almost about 80,000 or more enrichment, times of 80,000 or more times enriched, so that it will be available to us in the form of a resource. It does give us some few more insights that the processes. So that means when we will be looking at the different earth processes, that is what we basically try to correlate here, all the earth processes to formation of mineral deposits. Then we see that scarce metals like mercury possibly would be needing multiple steps or multiple stages of enrichment, so as to reach to a level where we can call them a resource, and the metals in between fall. They do also tell us, at least at the first end, that these metals will definitely take longer time to be available as resources in the earth. Now let me tell you that when we use the word resource, it is a much generalized qualitative term, representing the total for any particular metal or mineral. What actually it comprises is the mineral or the ore deposits. These are discrete entities present, that we see them and measurable in their quantity. They do satisfy some quality and quantity parameter, and the question is that where actually do we find them. So the answer is that we find them in the earth's crust, or to be more specific, in the upper crust. So what are the crustal domains in which we these ore deposits, these mineral resources, they occur in the crust, more specifically in the upper continental crust, either exposed on the surface or even going to depths as high as 5 kilometer. Quickly we can see what are the different crustal domains that we can expect to see such mineral deposits occurring. They will be occurring in recent or ancient sedimentary basins. They may be occurring in associated with magmatic bodies, subsurface intrusive magmatic bodies, in crustal scale brittle ductile deformation zones. It could be crustal scale as well as local scale deformation zones, such as shear zones, fracture zones, folded strata, and so on. And these sedimentary basin also could be the marine sedimentary basins or the fluvial and so on. So we will see them, the whole spectrum, in the due course of this lecture, and let us try to look at some of the basic terminologies. What do you mean by these mineral deposits that we are talking about is essentially constituting of some entity which we can call as an ore. So we define the ore as a natural aggregate. Ore is essentially a rock. It constitutes of natural aggregate of minerals, and the only specialty is that in the ore there is the concentration of either one or more than one element is above a threshold or a background value, which is called as a Clark value after the famous geochemist F.W. Clark. It's kind of an average value concentration in the crustal rocks. So these are examples of ore. This is taken from the iron ore. This is one of the photographs from the Hamersley Basin in Australia, where you could see the darker bands constituting of hematite, and the lighter bands, the red bands are the cryptocrystalline ferruginous silica known as chert. And in this, we all know that this black, this grey band, which is the iron oxide, is the material of our interest, and we call that, if that is the ore mineral, then the part which we would like to discard is the gangue mineral. This is a specimen of ore from Malanskhand copper deposit in central India, where you could see these as the sulfide minerals of copper in a matrix of quartz, and here this quartz is the gangue mineral and these are the ore minerals. And in order for this material to be qualified to be called as an ore, here we know that this concentration of metal like copper has to be above a certain value, say for example at least about 0.45% of copper to be, for this material to be called as an ore. So this ore, when we call that an ore, comes from something which is an entity occurring in association with common rocks in the crust, which is an ore body. This is an example of the ore body of copper from Malanskhand copper mine in central India, where you could see it's a rich mineralization of copper sulfide, copper iron sulfide chalcopyrite mineralization in this ore body. So the ore body needs to be present in a required dimension, length, breadth and width, and so that it gives us certain quantity of the metal for that to be feasible to be recovered by using our process, different scientific methods for extraction of the recovery of this particular metal. So this is the example. So when we see this is a typical look of a mine where an ore body is being exploited. This is taken from the Malanskhand mine, and if we want to represent the ore body in space, we can only do it on a geological map. So it's very important that if we want to understand the ore deposit formation processes, we do have to look at their maps at all scales. This is a mine scale geological map where the ore body, which is basically the copper rich ore body extending for a length of almost like 1.8 to 2 kilometer in surrounding rocks in association, as I told you that they occur in association with common crustal rocks. This is what is an example of a mine scale geological map. If we take a subsurface section of this ore body, we do see that it does extend to depths. That's what exactly what I mentioned, that this occurrence, sometimes they are exposed or they do extend to a great depth in the subsurface, variable depths. And when such ore deposit, they can either occur independently in one geological terrain, or there could be lots of such deposit occurring together. This is one example. This is from the Noamunde basin in Singhbhum Craton. In this particular basin itself, we get a good number of localities where the iron ore is being mined. In addition to that, there are many manganese. There are localities where the manganese ore is also being mined. This is an example where, this is an example of a place where there are several such ore bodies can occur in a small area of just about a square kilometer, which is coming from the Ekati diamond mine in Canada, and several such. So in those cases, we call them as ore district or mineral province or mineral belt or metallogenic province. There are many such examples of such kind of metallogenic province. The classic examples come from the Abitibi greenstone belt in Canada, Kalgoorlie gold district in Yilgarn Craton in Western Australia, Carlin Trent in Nevada, United States of America, where it's a very rich zone producing gold ores, and the gold bearing schist belts in Thorwald Craton. These are some of the examples of the metallogenic province or mineral belts. So we will continue discussing about these mineral resources in the subsequent classes. Thank you.